Hi, Emily.
Hi, nice to meet you.
Yeah, nice to meet you. I'm Jan. I'll be hosting today's talk.
Thanks.
And I'm actually a fourth year phys as well, even though maybe unfortunately for you, I've branched more into physics now. But
Oh, okay, fantastic. Yeah, it's a
I
great course.
yeah, and I think if anything could have kept me in philosophy, it would have been the philosophy of QM. So I'm really excited.
It is good fun. Yeah.
Yeah.
I mean, you'll probably know most of what I'm going to say, but I hope it will be interesting.
So we already have 13 people tuning in. That's pretty good. We'll probably wait for a few minutes past the hour until we get started. But
yeah, fair enough.
So you're tuning in from Cambridge, or?
No, I live in London at the moment.
You know, okay.
Are you at Oxford or at home at the moment?
I'm at home at the moment. I'm in Germany at the moment, actually.
Okay.
Hopefully I can return sometime soon, but
well, yeah, who really knows at the moment?
Yeah. Thanks for your nice comments, Miles. And yeah, thanks for joining in. So for everyone that's just joined, we'll maybe give it like a few more minutes until we're sort of 2 or 3 minutes past the hour, and then we'll get started.
I think you've disabled screen sharing if you want me to slide.
I think that might be Alexi who needs to do that. I'm not sure if I can. Okay, yeah. I think you should be able to share now. Yeah. Wow, 33 listeners, that's really good. Maybe 1 or 2 more minutes, but it's great that so many people have already joined. Yeah, I think let's get started. So today with us, we have Emily Adlam, who is a PhD student in the Department of Applied Math and Theoretical Physics at Cambridge. And currently she's working on relativistic quantum cryptography. Previously, she actually did her undergrad in Oxford, studying physics and philosophy, and having the pleasure, I believe, to be taught by David Wallace, who's sort of one of the most important proponents of a modern version of Hugh Everett's relative state interpretation. And she wrote her dissertation or her master's thesis on the problem of confirmation in the Everett interpretation. She then obtained another master's degree from the Perimeter Scholars International Theoretical Physics Program. And yeah, is now here to talk about interpretations of quantum mechanics, because I think contrary to belief, especially for a lot of physicists, there's actually a variety of ways to look at quantum mechanics. And there's still a lot of foundational questions and a lot of work to be done to understand quantum mechanics more thoroughly and more rigorously. And I'm really excited, and thanks so much for taking the time. And yeah, I'll hand over to you and feel free to get started.
Great, thank you very much. Thank you everyone for being here, and thank you for the invitation to talk about what to me is a very interesting and very important question. And I hope to convince at least some of you that it is indeed interesting and important. So I'll start by explaining some of the motivations that one might have for studying the interpretation of quantum mechanics. And I'll argue that this is not just a philosophical question, but actually an important scientific question. I'll then briefly mention a few ideas you might have heard in connection with this topic, which I do not consider to be adequate solutions. And then I will present three of the most well-known interpretations, and I'll describe some of their pros and cons. And finally, I will discuss a few interesting new directions in the field as of now. So first of all, why should you care about the interpretation of quantum mechanics? So the first thing I want to say is that the term interpretation is really something of a misnomer. So that's because interpreting quantum mechanics is not simply a matter of trying to gain a subjective feeling of understanding. Interpreting quantum mechanics is really about filling in some important incompletenesses in the theory. So the problem at the heart of interpretation of quantum mechanics, you might have heard referred to as the measurement problem. And essentially, the difficulty is that quantum mechanics has two entirely different formalisms. We have the standard unitary evolution formalism, and then we also have the non-unitary collapse formalism, where this collapse behavior is only supposed to occur during measurements. The difficulty here is that the theory doesn't provide any physical definition of what counts as a measurement, and therefore there's a whole lot of open questions about that. Does a measurement have to involve a conscious observer? Does the observer have to be human? Does that mean that unitary everywhere in the universe except on planet Earth evolution is unitary? All that seems odd and rather troubling, but we can put the problem in really sharp relief by considering some recent work by Froschiger and Brenner, where they set out a particular possible experiment where, depending on what choices we make about where to switch from unitary to non-unitary evolution, we can derive two inconsistent predictions for the result of a single measurement. So this experiment is not one that we can currently perform, but it is, according to quantum mechanics, at least possible. And therefore, the fact that the theory doesn't give us a definite answer as to what will happen under these circumstances is a pretty serious lack in the theory, and indicates to me that the theory is not yet complete and must be supplemented with a precise specification of when we ought to use unitary evolution and when we need to use the non-unitary Born rule evolution. So what that means is that the measurement problem is a genuine scientific problem, and therefore interpretations proposed to solve that problem are not just philosophical ideas, but rather specific hypotheses about the ways the world might be. And that means that, contrary to popular opinion, it is in fact possible for interpretations of quantum mechanics to make novel predictions, and there's no need for them all to be empirically equivalent. And we will see an example of this later in the talk. Furthermore, even in cases where two interpretations do seem to be empirically equivalent, it's nonetheless the case that they may present two very different ways of thinking about the theory. And that means they might also lead to new ways of thinking about how to proceed when extending the theory to new domains, such as quantum gravity. As you may know, we don't yet have a satisfactory theory of quantum gravity, and progress on this has been to some degree stalled for quite some time. And it's my view that this may well be because we based this research on an incomplete and incorrect understanding of the basic theory of quantum mechanics, and that we may well find that we make better progress on quantum gravity if we can come up with the correct interpretation of quantum mechanics. So for all these reasons, interpreting quantum mechanics is not merely a matter of intellectual curiosity. It is a serious scientific problem which has real consequences for the future of physics. So there are a couple of ideas which are frequently brought up in this connection, which you might have heard about, that I personally think don't do enough to solve the problem. So I'll just go through those now. So first, people have sometimes been known to say that the measurement problem is solved by the existence of decoherence. Now, decoherence is the mechanism by which, due to the spread of entanglement, macroscopically distinct branches of the wave function would be expected to become separated and to cease to interact or interfere with one another in any way. And this, I think, is the idea that behind postulating this as a solution is that if the macroscopically distinct branches don't interfere with each other, it's kind of as if there is a collapse, even though no collapse actually occurs. But this doesn't precisely solve the measurement problem that I set out, because it still doesn't tell us at what point the exact result of a measurement gets determined, and at what point we move from a superposition of different outcomes to the single distinct outcome that actually gets observed. So although decoherence does come in very useful for various interpretations, like the Everett interpretation, in and of itself, it is not a solution. You might also have heard of the Copenhagen interpretation. It's not straightforward to say precisely what the Copenhagen interpretation is, because it's really sort of a collection of different philosophical ideas postulated by Bohr, Heisenberg, and others, which are supposed to explain, to give various ideas about how we might think about quantum mechanics, or how we might make ourselves more comfortable with the apparent weirdness of the theory. And that, I think, is a useful and interesting project. But again, it doesn't solve the measurement problem, because it doesn't say anything specific about the mechanism of collapse and when we should expect that mechanism to operate. And finally, there's a way of thinking which again you might have heard of, called it from bit. It from bit is very popular with quantum information theorists, and it's basically the idea that quantum mechanics should be interpreted as telling us that the world is not really made of matter, it's actually made of information, and information is in some sense fundamental. I think this idea is again intriguing. There's interesting work to be done in this area, but in and of itself, this is not adequate as an interpretation of quantum mechanics, because information is normally thought of as being information about something, about the physical world. And so if you're going to suppose that information itself is fundamental, you're going to need to do more work to say what you mean by information in this context, and what information is if it is not about physical reality. So with those out of the way, let's move on to the first of, so this is called spontaneous collapse, and the basic idea of the spontaneous collapse interpretation is that the basic idea is that collapse is a fundamental physical process which happens everywhere in all sorts of systems, regardless of whether or not they're being measured. It's a spontaneous, random process that is taking place ubiquitously throughout the physical universe. So the most well-known version of this is due to Girardi, Rimini, and Weber, and they model the collapse by a Gaussian operator, which I've shown here. The result of operating with this Gaussian operator on the wave function is that after the measurement, or after the collapse, the wave function of the system will be very strongly concentrated about the location of the collapse. So we can subsequently think of that system as being localized at that point. So after the collapse, that system can be thought of as having a single definite state. The collapses are understood to take place according to the probability distribution I've shown here, which means that the probability of a collapse is proportional to the density of the wave function across the relevant region of space-time. And that means that the probability of collapse in a given region of space-time is equal to the probability that standard quantum mechanics assigns to us finding the system in that region were we to make a measurement there. So that link ensures that the collapse interpretation is empirically consistent with standard quantum theory. Now, the key observation for this approach is that if I act with this collapse operator on the state of a single system, what will happen is that the wave functions of all particles entangled with that system will also undergo collapse, which means that in a macroscopic object made of many thousands of particles, as soon as any one of those particles undergoes a collapse, they'll all undergo a collapse. And therefore, we can choose the parameter sigma in this equation in such a way that for a macroscopic object will with overwhelmingly high probability always be found in a single definite state. But at the same time, a single quantum particle can persist in a superposition state for quite a long time, which explains why we are still able to observe small microscopic things in superposition states. So this all works quite nicely. It makes sense. It explains why our measurements always show single definite results, because of course our measuring instruments are macroscopic objects, and therefore we will, with overwhelmingly high probability, always find them in single definite states. But there are, of course, some possible objections. One of these is known as the problem of tails. So the problem of tails arises from the fact that when I operate with this collapse operator on a wave function, it is, as I say, subsequently very strongly peaked about one location. However, it is also non-zero everywhere else. So in order to use this interpretation to say that the system is subsequently localized at a point, we have to add some rule which describes when a physical system can be said to be in some particular physical location. So the obvious way to do this is to say that a physical system is in a location, provided that enough of its wave function is inside that location. And that seems very straightforward. However, it leads to some very odd behavior when we consider possible compositions of physical systems. And that's because due to the way that the wave function for composite systems composes, we could end up with scenarios such that we have a set of particles. All of these particles are individually in a certain box, but it turns out that the collection of all the particles is not in the box. That's obviously not how we would expect the composition of physical objects to work. And therefore, it looks like we're going to have to find a different way of thinking about the locations of physical objects within this picture. An alternative proposal is to think about objects in terms of a mass density distribution over space-time. So we suppose that this mass density, that objects are associated with a mass density distribution such that the density at a certain point is proportional to the square of the wave function at that point. We can then simply say that an object is inside a given region, provided that enough of its mass density is inside that region. And because the mass density distribution is defined over space-time rather than over phase space like the wave function, this mass density distribution will compose in the normal way we expect of ordinary physical objects, so we won't get weird results with composite things. Another potential difficulty for the GRW for the spontaneous collapse approach is relativity. So the reason this is problematic is that with the mathematical approach that I've set out to you, when I perform my measurement, when I perform my collapse on the state of a single particle, the states of all the other entangled particles are meant to undergo collapse at the same time. But of course, within relativity, the notion of what at the same time just isn't well defined. So it seems to make this work, we're going to have to define a preferred reference frame on which the collapse can take place. But of course, that's very much in tension with the spirit of relativity, which is really, in a sense, all about getting rid of preferred reference frames. So if we want a relativistic version of the spontaneous collapse theory, we're going to have to do something a bit different. One possibility is to simply take a sort of equivalence class of space-time slices and say that rather than collapsing on a single space-time slice, the wave function collapses on the class of all equivalent space-time slices. And this does work mathematically, but it's quite hard to understand in physical terms what it would mean for the wave function to collapse on various different space-time slices at once. Another option is to move to what's called the GRW flash approach. And the idea here is to solve the problem by just getting rid of the wave function. So instead of a wave function and a set of collapses, we have a universe composed entirely of collapses. In Bell's poetic terms, in this picture, reality is simply a constellation of flashes. So because the flashes or collapses are simply point-like events, it looks like we will quite straightforwardly have relativistic covariance in this point of view. However, some care is required because we will lose relativistic covariance if we think of the flashes as being generated one by one in some sort of ordered causal process where the distribution of past flashes causes the distribution of future flashes. That's because as soon as we perform a change in reference frame, the causal ordering of the flashes will change. So this causal structure will not be stable under relativistic transformations. The solution to this is to move to an approach where we think of the flashes as being generated all at once in a sort of atemporal fashion. And that puts us in a somewhat odd position because the mathematics of the theory, the way in which we calculate the distribution of flashes, involves pretending that there is a temporal evolution and generating the flashes one by one in a temporal manner. But that can't be the ontology of the theory. So we have a sort of weird inconsistency between the mathematics, the structure of the mathematics and the structure of the ontology. And that to me suggests that although this is a really nice and intriguing idea, it can't be the final interpretation of quantum mechanics, because we really ought to be pushing forward and looking for a theory which incorporates this all at once atemporal approach in its mathematics. I will return to this theme, but for now, let's move on to the Everett interpretation. So I'm sure you're all aware of the Everett interpretation because it has always been very popular at Oxford. As Jan said, I did my thesis here with David Wallace, and this was an interesting experience because, as Jan says, David is a very strong proponent of the Everett interpretation, and my thesis was all about everything that's wrong with the Everett interpretation. So there was certainly some combative sessions, but I think that was all for the best. I think it was ultimately productive. So the Everett interpretation is, in many ways, the exact opposite of the GRW flash approach. The Everett interpretation says, let's keep the wave function and get rid of the collapses. So that means the mathematics of the Everett interpretation is simply the standard framework of unitary evolution that we all know and love. So the Everett interpretation is very simple, very elegant. It tells us that the theory is already correct and therefore no more work has to be done, which is no doubt part of its attraction. The obvious stumbling block is that if there is no wave function collapse, it looks as if whenever we make a measurement, all the results of that measurement must simultaneously occur. And that seems somewhat in tension with our experience, in which when we perform measurements, usually only one outcome occurs. So the Everettians have an interesting solution to this. Basically, their idea is that our conscious experience supervenes entirely on a single branch of the wave function. So when we perform a measurement, it's true that all the outcomes do occur, and there's just a different version of us in each of the branches observing all the different outcomes. So for this reason, the Everett interpretation is sometimes just referred to as the many worlds interpretation, because each of the branches can be thought of as behaving like a world in which different things occur. But I want to reinforce that all of these different branches are still part of the same physical wave function, which exists in the same physical world. So for that reason, I personally prefer to avoid the term many worlds. Now, as I say, this interpretation has a lot going for it in terms of its simplicity and elegance, but there are many objections that have been made to it. I don't have time to cover them all in detail, so I will focus on the issue which I personally consider the most pressing, which is to say probability and confirmation. So the difficulty with probability in the Everett interpretation is that it's quite hard to understand what it would mean to ascribe non-trivial probabilities to measurement outcomes within a picture which says that every outcome always occurs. A response that a lot of people make to this problem is to say something like, well, what the probability means is it's the probability that I will end up in a branch which sees a certain outcome. But that doesn't really work because, first and foremost, because there's no fact of the matter about which branch you end up in. There's a version of you in every single branch, and therefore when you observe a measurement result, you haven't learned anything new about the universe as a whole, because you always knew there would be a copy of you in that branch observing that outcome. Furthermore, a naive branch counting approach to understanding probability here doesn't work, because that approach would seem to suggest that when we do a measurement which has two outcomes and there are two possible branches, there should be 50% probability of seeing either outcome. But of course, we know that in quantum mechanics, it's perfectly possible to do measurements with two outcomes where the probabilities are not equal. And a naive branch counting approach can't account for these non-equal probabilities. So something more is needed here to explain how probability works within the Everett picture. One answer you might choose to make at this point is just to say, well, do we really need probability? Maybe we should just accept that in the Everett picture, there's no such thing as probability. But unfortunately, we do in fact need probability, and that's because the evidence for quantum mechanics is probabilistic in nature. So we came up with quantum mechanics, in essence, by looking at sequences of measurements, observing the relative frequencies of the measurement results, assuming that those relative frequencies in the long run closely matched the probabilities ascribed by the underlying theory, and then coming up with a theory which predicted the correct probabilities. So that process depends crucially on the assumption that probability is meaningful and that we really have seen a meaningful sequence of measurement outcomes corresponding to the probabilities that appear in the underlying theory. But of course, in the Everett interpretation, every possible sequence of measurement outcomes occurs. And so if we believe that the world is indeed Everettian, we have no reason to believe that the relative frequencies we've observed tell us anything whatsoever about the underlying theory of reality. So it seems that if we are Everettians, we shouldn't believe that we have evidence for quantum mechanics. But of course, we only became Everettians because we thought quantum mechanics was true. So it seems as if the Everett picture is just self-undermining. A slightly more philosophical way of putting this argument is to say that if you are an observer in an Everettian universe, when you observe a measurement outcome, the information that you gain is only self-locating information. You learn some information about where you now are located within this big universal wave function, but you always knew there would be an observer at that point of making that observation. So you haven't learned anything about the universe as a whole, and therefore that observation can never give you grounds to update any of your beliefs about the universe as a whole, including updates like confirming or falsifying a scientific theory. Now, the Everettians have proposed various different ways of dealing with this problem. Perhaps the most well-developed is the decision theoretic approach that due to Deutsch and Wallace. And so in this approach, we suppose that we have a set of agents within an Everettian universe who have to make some decisions. And we suppose that they're going to make their decisions in a way that is governed by certain constraints of rationality. Things like an observer should only care about the things that will happen in their own branch of the wave function. We put in these rationality constraints and do some calculations, and we can then show that the preferences of these agents can always be represented by the combination of a utility function and a credence function or degrees of belief function. We then further invoke a philosophical principle known as the principal principle due to Lewis. This principle says that objective chances or probabilities are simply those things which rational observers would set their degrees of belief equal to. So we can use that to argue that from this mathematical result, whatever the degrees of belief are within the preference description must in fact be the objective chances. And then finally, the final step of the proof is to show that in fact these degrees of belief must always be equal to the mod squared amplitudes that appear in the quantum wave function. That is to say, these degrees of belief must always be equal to the probabilities as ascribed by standard quantum mechanics. So the conclusion of the argument is that these mod squared amplitude values are in fact probabilities within an Everett picture. So this proof is very beautiful and very ingenious, but unfortunately, I think it doesn't work. And there's a couple of problems. The first is that these rationality constraints that go into giving the proof don't necessarily seem rationally compelling to everyone. So for example, the idea that you should care only about what's going on in your branch of the wave function does kind of make sense because due to decoherence, things which are going on in other branches of the wave function can never practically affect you. However, in real life, people frequently do care about things which are not directly practically relevant to them, and it doesn't seem as though doing that is obviously irrational. People can have different rational sets of preferences and different rational things that they care about. And there doesn't seem to be an argument to say that they're wrong to do that. And if we allow people to care about things outside their own branch of the wave function, then the whole proof doesn't work, and we don't get the mod-squared amplitudes out at the end in the way we hope to. Furthermore, even if you think the proof works, there's a further difficulty. There's a further question about whether these probabilities are sufficient to play the role of probability in the problem of confirmation. So that's because, at best, what this proof shows is that in an Everettian universe, it would be rational for observers to act as if the mod-squared amplitudes are probabilities. But the problem of confirmation is not about a problem about how it's rational to act. It's a problem about what is true. And the decision theoretic proof has given us no grounds to think that the observations we make tell us anything about what is true of the universe as a whole. At best, it tells us that it might sometimes be rational to behave as if we think the universe is such and such, which is not the same as giving us grounds to actually hold that belief. And so it looks like these probabilities, though they might perhaps describe rational behavior in an Everettian universe, can't possibly do anything to tell us about rational belief updating in an Everettian universe. So I don't think this decision theoretic approach does enough to solve the problem of confirmation. And in my view, the problem of confirmation is a sufficiently serious one that we must, perhaps with some reluctance, reject the Everett interpretation. So let's then move on to the final interpretation I wanted to talk about, which is the Broglie Bohm or pilot wave interpretation. So the basic idea of the Broglie Bohm interpretation is that in addition to the wave function, we have a set of Broglie Bohm particles. And these particles have definite space-time positions at all times, and they are pushed about through space-time by the wave function, which acts as a kind of guiding wave according to this guidance equation. So the key observation here is that when we make measurements, no matter what we take ourselves to be measuring, even if we think we're measuring spin or charge or whatever it might be, in the end, we always come down to making a measurement of position, because every measurement must terminate in us making an observation of the position of a pointer or a dial or some other measurement instrument. And that means that in order for our measurements to have definite results, it's enough for the Broglie Bohm particles to always have definite positions. As long as that's the case, then all our measurements will have definite results, even if nothing ever had a definite state of spin, charge, or whatever else it might be. So all the Broglie Bohm theorists have to do is insist that our conscious experience supervenes entirely on the positions of the particles. The wave function plays a role in our experience only by telling the particles where to go, and therefore, although the wave function can be in superpositions, we never observe any superpositions because our observations are based on the positions of the particles, which can never be in a superposition. So within this picture, the wave function, the guiding wave, evolves unitarily according to the usual rules of quantum mechanics, and it never undergoes any wave function collapse. However, we do get kind of an effective collapse, which occurs because you can show mathematically that after a measurement has been made, the behavior of the particles will subsequently be determined only by the branch of the wave function corresponding to the result of the measurement. So only that branch will be relevant going forwards. The other branches will still exist and will continue evolving unitarily, but they will be totally irrelevant to our experience from that point onwards. So from that point of view, even though there is no ontological wave function collapse, there is an effective wave function collapse when the right kind of measurement interaction occurs. So once again, there are, of course, some objections to this theory. First of all, there is, again, a problem with relativity. So that occurs because the mathematics of this approach says that when I make a measurement at a certain point, the wave function the guiding wave must be updated everywhere else in space-time simultaneously to reflect the results of that measurement. And so again, it looks as if we're going to need some sort of preferred reference frame on which that updating can occur. So the dialectic here is rather similar to the spontaneous collapse case. Once again, we have various possible options to solve this problem. We can take equivalence classes of reference frames. There's an interesting approach due to which involves kind of picking a preferred reference frame, not arbitrarily, but based on the way that matter is distributed through space-time. Or of course, we can take a route similar to the GRW flash approach, and we can just get rid of the wave function and say that reality is composed entirely of the particles, and the wave function is regarded as just kind of like a law of nature, which isn't really there in space-time and therefore doesn't need to collapse in any particular place. A further problem for this approach is the fact that the wave function seems to play two quite separate roles in the theory. So that's because in order for the mathematics to work and to reproduce the empirical predictions of quantum mechanics, it's necessary that at the start of the experiment, the de Broglie Bohm particles are in what we call quantum equilibrium. So that is to say, they're distributed across space-time in a way that is proportional to the mod squared amplitude of the wave function at those places in space-time. So that means that the wave function both defines the initial distribution and also defines the subsequent evolution. And to some people, this looks like a weird and unexplained coincidence, and they find this troubling and a reason to reject the theory. However, the Bohmians do have a really nice way of responding to that. And basically, the idea here is that if we take a generic initial state where the particles are not in quantum equilibrium, and then we allow the particles to evolve according to the standard guidance equation, you can show mathematically that in general, those particles will move closer and closer to quantum equilibrium as time goes on. So the idea is that the particles could have been in any random arbitrary state at the beginning of time, but since a great amount of time has passed since then, they've had more than enough time to evolve towards quantum equilibrium so that their state in the present day is so close to quantum equilibrium as to be indistinguishable. And this idea is actually really exciting because if the de Broglie Bohm particles were not in quantum equilibrium at the start of time, what that means is that you would expect to see some deviations from the usual quantum behavior at the start of time. And that's a thing that we could potentially pick up in our observations of cosmology, because as we know from the cosmic microwave background and so on, there are various signatures of the start of time which can still be observed now. So that means that the de Broglie Bohm theory actually makes some concrete predictions which are different to the predictions of standard quantum mechanics. We haven't yet been able to verify or falsify any of those predictions, but they are perfectly concrete scientific predictions, and therefore this is a nice counterexample to the idea that all interpretations of quantum mechanics are empirically equivalent. So let's take stock. As you may have inferred from my discussion thus far, although I think all of these approaches are very interesting and suggestive, I don't think that any of them is good enough, is quite right. I don't think any of them is the complete final theory. So let's have a look at some new, let's see where they might point. So first of all, there's an interesting move in recent years in the field towards rejecting traditional interpretation in favor of axiomatization. So the idea of axiomatization is that we can derive quantum mechanics from a set of simple physical principles, and the idea is that once we've done that, we will have done all the explaining that's necessary, and the job will be done. And this approach might be of particular interest to this audience because many of these approaches are based on information theoretic ideas. So for example, there's a really nice axiomatization due to Marcus Muller and some collaborators, where they derive the formalism of quantum mechanics from the axiom that there exists a single fundamental unit of information. So this approach, therefore, is kind of an interesting way of cashing out this idea of it from bit that we saw earlier, and describing what precisely we mean by information in this context and what role information plays in relation to our experience. the problem with these axiomatic approaches at the moment is that most of them take measurement as a concept, as a primitive, and therefore they don't yet provide a solution to the measurement manifested physically and when this process of measurement is supposed to occur. But I think that's a thing that may well be rectified in the future development of the theory of the field. And this is an interesting direction which might well lead to some new ideas in interpreting quantum mechanics. I myself am also very interested in approaches which involve alternative temporal structures. So we saw we've seen three interpretations of quantum mechanics so far, stood in a sort of very standard temporal picture where you start rather like a computer which takes an initial step. We discussed the GRW flash approach, that when it comes to trying to make things relativistically covariant, there are very good reasons to consider getting rid of that picture and instead moving to an approach where we have kind of atemporal all at once laws which apply to the whole of history and define things instantaneously all at once, rather than taking a state and evolving it forwards in time. And indeed, I have a paper on this subject where I argue that if you believe in the existence of spatial non-locality as implied by Bell's theorem, and if you want to have consistent non-locality, and once you move to temporal non-locality, it's very natural to then move one step further and go to this all at once atemporal approach. So in my view, this is where the future of the field most probably lies. And there's a bunch of really interesting work in this direction, developing non-standard temporal approaches to quantum mechanics. So one point is that in this sort of all-at-once atemporal approach, one would naturally expect to see manifestations of something that looks rather like retrocausality, that is to say, causation from the future towards the past. And there's been some very interesting work by people like Wharton, Price, Busey, and Leither, trying to understand what causality looks like in quantum mechanics. Price, Busey, and Leither have some proof to the effect that if you want to have time symmetry in quantum mechanics, you necessarily have to have some type of retrocausality. There's also some very interesting work by Reshkov and Giamazzi on what they call the process framework. And this is an approach which aims to give us a way to describe quantum correlations in a way that doesn't depend on any predefined causal order. So the idea here is to move away from the picture of things evolving forward in time and allow us to describe more varied and non-standard causal pictures. So as I say, it's my view that the future of the field probably does lie somewhere with one of these sorts of alternative temporal structures. And I would also observe that if it is indeed the case that the correct interpretation of quantum mechanics involves rethinking our ideas about what the relationship is between quantum mechanics and time, that might well explain why we've had so much difficulty coming up with a quantum theory of space-time. Because if we have misunderstood how quantum mechanics works with relation to time, then in order to come up with a theory of how quantum mechanics is manifested in space-time, we probably need to go back to quantum mechanics, rethink that temporal relationship, come up with an interpretation which correctly represents that relationship, and therefore we're likely to make more progress on a quantum theory of gravity using that approach. So I hope I have said enough to convince at least some of you that the interpretation of quantum mechanics is both interesting and also a genuinely important scientific problem, which is likely to have important consequences for the development of future science. I'm very happy to recommend some resources if you're interested in learning about any of the approaches I've discussed here. And I'm also very happy to now take some questions.
Thanks so much, Emily. That was really interesting and very, very comprehensive. I think you summarized the Oxford Physics and Philosophy QM lectures in an hour. So I think one thing which I would find very interesting is I've created a doodle poll where you can select your favorite approach to understanding quantum mechanics. And I'm going to post a link in the chat and see what people think and what sort of the popular opinion is.
Cool.
And yeah, I think it would be nice to turn to some questions, and we've had a lot of questions in the Q&A section already, and keep them coming in. So I think I'll start at the top, which is something related to the GRW collapse approaches.
Yep.
And Andres Chikizaya, I think I'm just going to read out your question because I can't give you permission to speak right now. And he asked that if we measure something, will this cause that single particle states overlap?
Sorry, will the GRW?
Maybe I can see if I can give him permission to speak so he can formalize his question. Okay, I can't, unfortunately, don't have the permission to let him speak, but I'll just repeat the question again. He asked, if we measure something, this will cause that single particle states overlap. Maybe what he's trying to get at that if we perform a measurement and we get this Gaussian,
Yes.
will this basically, because of the tails of the Gaussian, because you're not perfectly localized, will that cause for there to be overlap between different single particle states? Maybe that's what he's asking.
Yes, well, yes, because then naturally there would be, because a position state, any position state which is not perfectly localized will have some support on the whole of space-time. So all pinnacle particle states will have support on the whole of space-time. It's just that most of their support, in most places, the wave function will be very small, and so while in effect they will be concentrated at a specific location, they will also overlap in all the other places where they have some support.
Yeah, if that's not clear to you, Andres, maybe just post in the chat to follow up. The next question we have is from an anonymous who's asking that maximal entanglement is monogamous, right? Could you please comment on why collapse of a single bit in the macroscopic object would imply collapse of the wave function in the whole system?
Great, yes. So this is essentially because of decoherence. And so what we find is that when we try to describe the quantum states of macroscopic objects, because interaction is so ubiquitous, entanglement spreads very quickly through the system, and so given in any macroscopic object, all of the particles in it will be entangled with one another. And as you say, maximal entanglement is monogamous, so they won't be maximally entangled with each other. In general, they'll have a small amount of entanglement with a variety of their neighbors, and each of their neighbors will have a small amount of entanglement with the other neighbors, and so the whole system will be linked by links of non-maximal entanglement. But the collapse will occur as long as the two particles share any entanglement at all. It doesn't have to be maximal entanglement.
So the next question is from Rifat Khan, and I think we can give you permission to speak if you want to, so you can ask your question yourself. I think you're still muted. Oh, maybe he isn't there. Okay, maybe, are you there, Rifat? Okay, I guess I'll just read out the question. So Rifat is asking, why can't I say collapse happens with respect to reference frames? I think that is related to the special relativity objection of the GRW collapse approach.
Mm-hmm. Yes. Why can't you say collapse happens with respect to reference frames? Well, the idea of in the GRW picture of collapse is a physical process which happens at a physical location. And if that's the approach you're taking, you need to say at which physical location does it happen? At which space-time point does it happen? So you have to select a space-time point on which it happens. So therefore you have to select some reference frame, and there doesn't seem to be any natural reference frame to select. Selecting one reference frame is tantamount to choosing a preferred reference frame, and while that's not mathematically while that doesn't lead to its frame, that does seem very much contrary to the spirit of relativity, which is very much against having preferred reference frames. So although that wouldn't lead to any although choosing a reference frame doesn't lead to contradictions, it looks messy and it doesn't look like a good way of uniting quantum mechanics with relativity.
Right. I think we have another question from Abhinav Chudori, who I think has 2 questions. So if you want to maybe come forward and ask those questions. Oh no, he's not in the call anymore. Okay, I'll just ask them on his part. So the first question, I think it's a bit tangential, but we can ask it anyway. Is string theory a theory of quantum gravity?
Yes, it is. Not yet a hugely successful one in terms of making any new empirical predictions, but it is a theory of quantum gravity which does a great deal of ingenious things and may one day produce new empirical results, we hope.
And then the next question is, can quantum mechanics explain the mystery of neutrino oscillations?
I think the mystery of neutrino oscillations remains an unsolved problem, to the best of my knowledge. I wouldn't necessarily expect it to be explained within standard quantum mechanics. It seems like you would need at least quantum field theory to explain neutrino oscillations.
The next question is from Mohammed Alham. Can we give him permission to speak? So you can ask a question yourself. Mohammed, feel free to ask your question. Yeah.
Hello. Can you hear me?
Yeah, I can hear you. Yeah, I can hear you.
Oh, okay, all right. So, hello, Dr. Emily. I would like to ask, if someone asks you which interpretation you would prefer, what would you answer them and why?
Yes. So, as I said, I don't personally favor any of the sort of standard well-developed interpretations, basically for the reasons I've discussed during this talk. I don't think the Everett interpretation can work because I don't think we can overcome the problem of confirmation. I think the Broglie Bohm and GRW do interesting things, but I think that they're somewhat awkwardly trying to accommodate a spatially local and spatially and temporally local theory within a context which doesn't really look very spatially and temporally local. So my preferred option is to move towards the sort of non-standard temporal picture that I've discussed, with some sort of all at once atemporal theory. There are various results in this direction, but there isn't yet a well-developed interpretation which I can point you to. But this is quite a new area which direction that the field is moving in, and I hope to see more interesting results in the future.
I think the next question is, which I guess applies for most people wishing to learn more about interpretation of quantum mechanics, which is, what resources would you recommend for someone starting to learn about quantum mechanics?
Quantum mechanics or the interpretation of quantum mechanics?
I'm assuming this is probably aimed at interpretation of quantum mechanics.
Yes. Well, what I can recommend is my book on this subject, which is coming out in February. So I wrote a book on introducing the foundations of quantum mechanics, which covers both interpretations of quantum mechanics and other subjects, which will be available from Cambridge Elements very soon. That gives it quite a fairly comprehensive, that gives much of what I've said I've said in this talk will be repeated there, and there are further resources. Where to look depends on which particular interpretation you're interested in. If you're really into the Everett interpretation, David Wallace's book, The Emergent Universe, is a great resource, very comprehensive, and sets out the decision theoretic approach in great detail. If you're interested in the sort of atemporal approaches that I've discussed, I would recommend the work of Ken Wharton, the work of Matt Lether and Matthew Pusey. What else? The spontaneous collapse interpretation is set out quite clearly by Girardi, Rimini, and Weber in their original paper. there's various sort of foundational texts for each of these specific interpretations, although I don't necessarily know of a single resource which will cover them all in the kind of detail you might want. So I would tend to go to the work of the proponents of each of the interpretations to get the details on what they would say.
Yeah, I think I would only add maybe that a book that maybe isn't particularly charitable to the Everett interpretation, and which is sort of more inclined to argue for GRW collapse theories or the Broglie Bohm theories, is Tim Maudlin's Philosophy of Quantum Mechanics, which I think is a good sort of first introduction to the field because it's not so heavy on mathematical formalism, like for example the imagined multiverse, which is very, very comprehensive.
Yes, Maudlin is very readable and somewhat idiosyncratic, but yeah, he's very opinionated. But
yeah, that is true.
Yeah.
And then the next question is from Hamish Todd, who's asking, maybe I'll just let you ask a question yourself.
Yeah.
No, sorry, I can't give him. No.
Yeah. Hello, you can hear me now.
Yeah, I can hear you now. Yeah.
Okay, brilliant. And I forgot what my question was. No. Okay. So you made the case that that we can do some empirical. We can address these questions empirically. My question is: suppose that the counterfactual that it turns out that we can't do the cosmic microwave background radiation de Broglie Bohm experiment that you mentioned. And there was another one that you said as well at the beginning that was related to the something.
Renner paradox.
Yeah, that one. Suppose it turns out that we can't do those.
Yes.
And be a bit pessimistic if you don't mind, and suppose that we don't get much more. We don't get any more empirical confirmation. Does that mean that the philosophy of this of quantum possibilities becomes less interesting? And parallel to that question, does the term interpretations of quantum mechanics become sort of a better, more descriptive term for what we're discussing here?
Yeah, interesting. I think the reason I'd say that interpretation is not a great term is essentially because the question at issue is not just how should we think about the theory. It's what happens in this specific physical situation. So I think the term interpretation kind of suggests that there's no fact of the matter, and we're just trying to kind of think about how we should understand things. And even if we can't test which interpretation is correct, I think nonetheless there must be a fact of the matter about which one is correct. And so it would still be inappropriate to think of them as interpretations, because physical questions that we can't answer remain meaningful physical questions. And I think even if we can't directly test interpretations, they still have scientific relevance because, as I've said, the way you think about quantum mechanics will influence the way that you think about how to go on and do other things like quantum gravity. So, for example, if you think the quantum state is ontic, if you think it's an element of reality, you're probably going to want to do quantum gravity by quantizing space-time, as in the sort of canonical approach to quantum gravity and string theory. Whereas if you think that the quantum state is not ontic and it's just a description of our knowledge, then you're more likely to do quantum gravity by trying to derive space-time out of some underlying substratum, as in causal set theory. So I think that figuring out the correct way of thinking about quantum mechanics is almost certainly a helpful approach in terms of working out what to do next, even if it's never directly testable.
Thank you.
So we have 3 more questions in the chat. The next one by Mohammed Elham. Can we say that the analogy of trying to interpret quantum mechanics is like, oh no, sorry. He's been given audio permission. Do you want to ask your question? Can you hear me?
Yes, I can. I was just thinking of this like simplistic way. Can we say that trying to interpret quantum mechanics is like some sort of a blind man trying to explain what elephant is to each other? Is that like some sort of a compatible analogy?
Yeah, that's not a bad analogy at all, because I mean, what we're trying to do is we're trying to interpretation can be a bit like trying to find metaphors. It's like trying to describe what's going on in terms that are familiar to us from our macroscopic experience, but there's no obvious reason to expect that like the true underlying net stuff of the universe to be very similar to our macroscopic experience. So there is a real obstacle of how can we even conceptualize what's going on when we only have conceptual resources based on our usual macroscopic experience. So yeah, that is very much the problem, really, that the inability to conceptualize stuff that is things that are very outside our everyday experience.
Then we have another question by Rafat Khan. Yeah, should be here.
Hi, can you hear me?
Yes.
Yeah.
Yeah. Shouldn't we have an interpretation of quantum mechanics in which we don't have this observer and system split, because observers can also be described by quantum mechanics? For example, like the things that they do when they talk about wave function of the universe or something.
Yes. Yeah, exactly. That is exactly the point of interpreting quantum mechanics. The idea that we must be able to understand what an observer is and what the process of measurement is in physical terms, and therefore we must be able to say within our theory what is going on in a measurement in physical terms. And so none of the interpretations which I presented to you have an observer system split in the usual sense. So in the collapse interpretation, observers are just made out of collapses like everything else. There's no distinction between observers and non-observers. In the Everett interpretation, the wave function is universal. Observers are just made out of the wave function like everything else. And in the Broglie Bohm theory, observers supervene on particles and non-observers also supervene on particles. Again, there's no observer system split. So yes, you're exactly right. That the idea of interpreting quantum mechanics is to get rid of the observer system split.
And is it also right to say like even clocks are made up of stuff to which QM should apply? So we should not single out time being different, something like that?
Yes, and that is essentially the problem with quantum gravity, because time is one of the few things that is not quantized within quantum mechanics, and we don't know how to quantize it. The problem with quantum gravity is at heart about understanding how to understand time within quantum mechanics.
Okay. And in this interpretation with which they talk about wave function of the universe, over there, would you say that there is no notion of collapse in it? Like there are only correlations between the observers and the system that they study?
Yeah, the wave function of the universe is most commonly talked about in the context of the Everett interpretation, because the Everett interpretation doesn't use collapses. Therefore, it makes sense to think of there being a single wave function of the universe. You do also have a wave function of the universe within the Broglie Bohm theory, because also in that picture there are no collapses, but you do in that picture have effective collapses due to the way that the particles move. Within the spontaneous collapse interpretation, it doesn't really make sense to talk about the wave function of the universe, because either you're the GRW flash, in which case there is no wave function, or you have wave functions, but they are frequently collapsing and splitting and not holistic in the sense that the universal wave function would require.
Okay, thank you.
So the next question is, if a pair of entangled but distant particles are taken and one is interacted with, are there any models or interpretations in which the communication between the entangled pairs is not instant but accounts for the difference of reference frames? If so, how exactly?
So in a sense, the communication must be instant in order to get the empirical results right, because when you measure your entangled particles, no matter when you make those measurements, the relationships will be the same. So there's no delay in which the information reaches the other particle. The only way to really get around that is to eliminate non-locality altogether. It's sometimes argued that the Everett interpretation does this, and that kind of the non-locality is encoded in the universal wave function rather than in communication between the particles. some people have also suggested that retrocausal interpretations can do this, but by rather than having instantaneous communication, we have information being sent via the future. So there are possible ways to get rid of instantaneous communication, but you can't possibly have delayed communication.
Okay, yeah. Then we have two more. How do temporal non-locality models treat the question of causality and ensure that causal order is maintained?
So I think within a temporally non-local model, one would be inclined to think of causation as an emergent phenomenon. So rather than being a fundamental feature of reality, it kind of appears at a higher level as a result of the way that we interpret the physical reality that we find ourselves in. So causation in that picture would not be the sort of fundamental physical thing that we think of it as being in standard temporally local pictures.
And one last question, which I think is very interesting. Could quantized time be realized in quantum mechanics as the transfer or update of one unit of information?
Yes, that's an interesting idea. I think I would have the same objection as I have to the standard from bit view, in the sense that if you want information to be fundamental, you need to say something quite strong about what you understand information as being, if information is not about anything. And otherwise it looks as if you're just using the term information, but in fact referring to something else entirely. So while that's an interesting idea, I want to see more elaboration of what exactly the information is about, or how we can understand information that's not about anything.
I know we're running over a little bit, but would it be fine to go for a few more minutes? I have actually two more questions. So the first is directly related to your objection to the Everett interpretation, which I hadn't really come across before, but I think is very, very interesting. And I was just wondering what sort of necessary commitments from the philosophy of science it requires, because the way I would, for example, think about this is that someone who objects to your interpretation, who is an advocate of many world theories, could just say, well, but we're not really interested in establishing objective truths about the world, or that this isn't necessarily what we need for our interpretation to work. And I think also a key point in your objection is that we can't establish reference to the theoretical entities of quantum mechanics. But then I think there's definitely positions in the philosophy of science where even speaking of theoretical entities is sort of meaningless. And if we can speak about them, then only in the context of doing measurements and experiments. So I was just wondering what sort of philosophy of science nuances we get into, and what sort of commitments are required for your objection to go through.
Yeah, so there's a couple of two different points there, really. First is, should we care about establishing objective truth? I don't think you necessarily need to describe it under the heading of objective truth, but if you're going to be an Everettian, you have presumably based that on your belief that quantum mechanics is correct, because otherwise there would be no reason to be an Everettian. And your belief that quantum mechanics is correct is based on quite strong assumptions about the nature of the evidence that we have for quantum mechanics, in particular the probabilistic nature of that evidence. So if the Everett interpretation undermines the evidence that we have for quantum mechanics, it looks like it's a position that just can't be sustained, because without having evidence for quantum mechanics, we have no reason to be Everettians. So I think kind of the very basic thing any interpretation must do is tell a coherent story about how we're related to the evidence that we have, and how that evidence gives us information about what the interpretation says is in the world. And if your interpretation can't do that, it just can't be epistemically rational to believe in it. The second question is about theoretical entities, and I agree that many physicists and philosophers don't like theoretical entities and don't want to talk about them. But that's primarily an anti-realist view, and the Everett interpretation is mostly treated as a realist interpretation, in which we are saying real things about the world and describing real theoretical entities. And so if you are a realist, if you are a standard Everettian who regards your view as a realist approach to what there really is in the world, then you seem to need to have some way to explain how we get to know about those real things that you're claiming exist. And again, I think the Everett approach doesn't allow us to have any pathway to know about the things that the Everett interpretation claims are in reality. And so again, there's no epistemically rational way to justify the beliefs we're supposed to have within the Everett interpretation.
Great, thanks so much. So basically, an Everett could be an anti-realist and then could avert the objection with regards to the theoretical entities.
Yeah, I mean, I'm not sure what it would mean to be an anti-realist and an Everettian, because the Everett interpretation is a hypothesis about the contents of
The
reality.
of quantum mechanics.
So if you're an anti-realist, you presumably don't need to interpret anything, because you can just take an instrumentalist view and say the predictions are the predictions. We don't care what underlies them.
Yeah. Okay. And my last question is: do you still think the measurement problem is at the heart of understanding quantum mechanics?
Yeah, I mean, I think the measurement problem is a good way in. I think once you start thinking about the measurement problem, you discover a large range of related problems, such as the difficulty of getting consistency between spatial non-locality, relativity, and temporal locality. So I think I wouldn't necessarily describe the measurement problem as the only problem or the most important one, but I think it's kind of a really good entry point, because it's a really obvious place where the theory, where there's a lack in the theory that needs to be filled with something.
Okay, I see. Yeah. Quick update from the poll. I think the Everett interpretation is actually leading with 7 votes.
No.
3 votes to the alternative approaches and 1 vote for the Broglie Bohm theory. But maybe that'll change in the future if better alternative theories are developed. I think maybe to conclude, one final question from the Q&A. Can you conclude different experimental outcomes with different interpretations of quantum mechanics?
Yeah, so as I say, there's some different predictions from the Broglie Bohm interpretation in terms of the various cosmological observations. We haven't made those observations yet, but hopefully we will one day. And as I say, there's also the Fraustiger-Renner paradox and various other related experiments which involve basically trying to put people in superposition states and seeing what the outcome of that would be. I mean, again, we don't know how to do that, but in principle, it's possible. And the different interpretations will say different things about what the results of those experiments would be if we could do them. And of course, there may be other interpretations we haven't yet thought of, which make other novel predictions that we haven't yet made.
Yep, great. So thanks so much, everyone, for listening, and thanks so much, Emily, for taking the time. I think it was fascinating, really interesting, and a bit of a light at the end of the tunnel for me, because I'm a bit of a reluctant Everettian, but I hadn't really seen a really pressing objection yet, and neither had I been introduced to any alternative approaches to understanding quantum mechanics. So yeah, thanks again, and thanks everyone for joining in, and yeah, have a great evening.
Thank you very much.
Thank you. Bye.
Bye.